this lecture. The first one is prepared by Marit and the second one by myself. And the topic is stellar dynamos. And the first part is mostly about observations and going briefly through some techniques called Doppler imaging, with which we can map the temperature on a surface of a star. If you have star spots or something like that, then you can see those in the spectra of the star. And then a similar method is the Zeeman Doppler imaging, where you can also determine the magnetic field of the surface of the star. And then there's some results on surface differential rotation inferred from various observations of different stars. And then some implications for dynamo models. And then the second part is actually what I have done, and it may or may not contain all of these items. Probably not the last one, at least. Okay, so a few words about Doppler imaging. So if we have cool or hot spots on the stellar surface, then they can, or they will give a signature to spectral lines. And especially if these lines are sensitive to temperature differences. You have, of course, millions of lines in the stellar spectra, and some of them are more sensitive to temperature changes than the others, and some are then more sensitive to magnetic field changes, which can be used to map the magnetic field. And then there are some conditions where you can use this method, and first of all, you have to have a high enough rotation rate so that your lines have to be broadened in order to see these features in these spectral lines. But they have, if the stellar rotation is too fast, then the lines are so wide that it's not possible to use this method any longer. And also the inclination of the rotation axis matters when you can use this method. Okay, so there's now an animation by Oleg Kochukov, as I'm showing in this place. I can remember which one it was. So you have some spots on some synthetic spots on your synthetic star. Then you look at the line profile. So you can see this bump coming from the left, going to the right. So first you see this on the blue side, and then on the red side of the spectrum line. Okay, so this is kind of basic. And then you can, in principle, then determine the longitude and the latitude of the spot from these changes in the spectral line, and the temporal behavior of the distortion. And of course, this is this is an inversion problem, which is not uniquely defined. You can have many solutions which reproduce your observation as well. So it's kind of an ill-posed problem, and you have to minimize some discrepancy function, and you have to have a synthetic spectral line with which to compare your observations. But in principle, this is the process how you can do this. Okay, then what is Zeeman Doppler imaging? So in addition to the previous effects of temperature, then if you have magnetic fields on your star, and you usually have magnetic fields, they will polarize the light. And by the Zeeman effect. And then you have to actually do what is called spectropolarimetry. So you observe in polarized light. And then in principle it's possible to get a signal with all of the four Stokes components. And these different components are sensitive to different kind of magnetic fields. So the circular polarization is sensitive to the line of sight component of your magnetic field, and linear polarization is sensitive to Stokes Q and Q signatures, and these are this is linear polarization. And there's a couple of more animations on this, all by Oleg. So this is now Stokes E. So this is the circular polarization, and then you see different sorts of magnetic fields. These are horizontal on the surface, and here you have a radial field. So let's see that again.
But there are no pairs of spots, right? It's not like in the sun. Right?
No, this is not a real star. This is just purely synthetic, just to demonstrate how the spectral features change. So you don't have any kind of bipolar regions in this. It's kind of a toy star in that sense. And then the last figure, this is kind of a spherical hedgehog that you have. And then you see all of the Stokes components, I, V, Q, and U. And then in principle it's possible to see these features in the spectral lines of the stars, which have magnetic fields. So we'll watch this once more. And but of course this is a highly complicated process. So if you previously had only one feature that you were looking at in your spectra, now you have many more. And there's some results, just some examples. This is now a temperature map of a star called II Peg, and this has been observed for a long time, now 18 years. And what is typical of this, this is a solar-like star, but much younger, so it's rotating much faster than the sun is. And here in the middle, this is the pole of the star. So you are seeing these maps pole on. And you see these large dark spots which are at very high latitudes. I think this is now I'm not sure if it's 75 or 60 degrees, the first circle. And you see that they cover a very large amount of the surface of the star. And you also tend to see that many times these plots have they're separated by 180 degrees in longitude. But of course, in some other cases, you see that there is kind of lots of these things. It's very not very easy to say which one of these is the strongest one, and whether this actually is real. Probably this is a large star spot region which is just blurred out in these observations.
Okay. What's the resolution of the method? What is the smallest sunspot? This both with respect to the area and the magnetic field. Is it detectable?
That I don't actually know. I have to admit.
resolution, the smallest spot.
Yes. For example, can this spot be, in fact, well, for example, one this spot be a collection of smaller spots?
Oh, but it must depend on the width of the line, therefore on the rotational broadening. No, not. I mean the summit broadening, of course.
Yeah.
But the phase is known with high accuracy, right? So the resolution can be quite high. What limits the resolution? There will be inversion, of course. There will be some uncertainties related to the inversion, correct?
I mean, when we know that we can't do that with very slowly rotating stars.
Okay, sorry.
Yeah, that's, I cannot really, it's better if I don't make a statement regarding how small
You also don't know, yeah?
because somebody will...
No, do you know
Sorry, what?
the answer?
Answer of
What
each
limits
of those
the resolution?
Signal to noise ratio should be 200, actually, if you want to have
So it's a
smaller
noise.
spots.
Okay, so it's a signal to noise which
Yes.
limits it. That's interesting. Okay.
Okay, thanks. And, okay, then you can use also other methods. You can monitor the brightness of the star for over a long period of time, like here, starting from the 1970s and going to, well, here until something like 98. And you can also see these spots on the light curve of the star. And in that analysis, then you can also see that you have, if you take the simplest possible assumption that you have two spots, well, simplest after the one that you have only one spot, and then you can play around with the how strong these spots actually are. What is the temperature of those spots? And then you see that if you just plot the strongest spot and the weakest spot, and you see that after some time they seem to change position. So that the idea is that you have these two spots which are separated by 180 degrees longitude, and then at some point the strongest spot moves to the other longitude and the weakest spot goes to the previous one. And this seems to happen somehow periodically here in this star. And similar stuff has been seen also from Doppler images. The last points here are from Doppler images. So you actually see the spot and then you determine which one is the stronger and which one is the weaker. And then you can, in principle at least, see that there is a singular effect, which is called flip-flop. And this is interpreted to be something like the solar cycle. But of course the magnetic configuration of the star is totally different. However, now Mariana is involved in doing a reanalysis of this same star with the same observations, and it seems that it's not so clear any longer what happens. I mean, here around between something like 95 and 97, there seems to be flip-flop, so one of the strongest spots goes to the other longitude, but then where we would expect to find another flip-flop, then it's not so clear what happens. It seems that the spots kind of meet and then they go away again. So at the moment this is also being checked from photometric observations over a long period of time. So there seems to be some discrepancies already at this phase. And then if we look at this is the same star again from 2004. These are now Doppler images, where you simultaneously get the temperature map and then the magnetic field. And if you compare these two figures, you don't really, you cannot really associate the places where you have strong magnetic fields with those where you have a star spot. And one possible explanation is that the lines that were used in these maps were really sensitive, more sensitive to magnetic field than to the temperature. But still, this is kind of an strange result. Why do we see something like that? Okay, and then there are other possible reasons why this might not, why there might be some complications. However, this is not all. There's that's an independent method by Torsten Karel and collaborators, where they use a different approach to the problem. The previous map usually uses just a few lines, something like of the order of half a dozen maybe. But here they take hundreds of lines and use all of those in their inversion. And at least for this particular case, now unfortunately I don't know from which year this is, they do see that there is a kind of a bipolar pair of spots at the polar regions, which would be of course nice, because this is what the very first maps showed, the temperature maps showed, that you have two spots with high latitudes. However, it's not yet clear what happens to these spots when you have a flip-flop. So does the polarity of these spots change, for example? That would really constitute something like an analog of the solar cycle in these more rapidly rotating stars. Okay, now this is the third independent method, which also uses Doppler inversions, and they also use several hundred lines. But now the treatment of these lines goes via this LSD process, which is least squares deconvolution. So I do not actually know any of the details of these methods, but the results look quite different to what the other groups are getting. So this is now the azimuthal magnetic field, and this is the radial magnetic field. And it seems that it's very easy to get these very large patches of strong azimuthal magnetic field on the surface of the star. This is not the same star, of course, but anyway.
The two plots, radial and azimuthal.
Yeah, this is radial and this is azimuthal. And the latitude is
And by the way, does it matter whether it's in the positive or negative phi direction? Could be the same, yeah? Or would you actually see a different sign then?
Wait a minute, maybe this. It is actually, this is, I mean, the red would be plus and blue would be minus.
Yes.
So it's in the negative direction.
Interesting. Anwar, pretty crazy, yes?
Yeah, it looks interesting.
Yes.
And okay, then we have a double slide. And then this is another synthetic exercise. This was done by Torsten Karel again. So in the topmost row you have a synthetic observation, or synthetic star, map of a star. So you have a pair of spots at high latitudes. Then you do your inversion, where you simultaneously invert for the the magnetic fields and for the temperature. And then on the bottom line you see the same thing, but you keep your temperature constant. Then you see that you don't see basically any radial magnetic field, but you see these azimuthal structures. And if you compare these two inversions, then these both give an equally good fit between your initial profile and then your synthetic one. Okay, so then I have some slides about differential rotation on these rapidly rotating stars. So, or in a bunch of stars, not necessarily rapidly rotating. And these authors usually find this kind of relation. You have the absolute differential rotation divided by the differential rotation itself. And this is usually then given by a power law, omega 2 power minus n. And from observations you get something like n is close to 1. Which means that your absolute differential rotation is almost independent of omega. And there are similar results from theoretical models where you solve for the differential rotation profile of different types of stars or with different rotation rates, and there you have a slightly larger index, but that is not too much different. So what this means is that the absolute differential rotation stays pretty much constant as a function of rotation rate. So if you just ramp up the rotation rate, then you still have some differential rotation. And this absolute differential rotation is what matters in the dynamo models. So the conclusion is that it's probable that the differential rotation plays a minor or a decreasing role as the rotation rate of the star increases. Okay, then if we look at the dynamo number, which is this guy here, I will talk a bit more about this in the next part. And here alpha is our usual alpha effect and E/T is our turbulent diffusion. And then the question is, how do these turbulent quantities behave as a function of omega? And observationally we know very little. We do have some results from convection simulations, and one thing that we find is in these numerical simulations that alpha tends to increase as a function of omega and eta-t tends to decrease as a function of omega. And then the omega effect, as we saw on the last slide, is roughly constant. So we would expect the dynamo in the sun we have what we call an alpha omega dynamo, where alpha produces the poloidal field and omega for the differential rotation the toroidal field. Whereas in these rapidly rotating stars, alpha actually also contributes to generating the toroidal field and can actually be even stronger than the differential rotation. Okay, so these are now the conclusions for the first talk. So, okay, we know that we can, in principle at least, observe magnetism on other stars with spectral polarimetry, and but there are some important things that we should also learn more from these methods. One of them is this polarity of these active longitudes. Does it change when we see this change of the magnitude of the spots? Okay. And then it would be very important to see connection between magnetic field and temperature. So we should have observations with both magnetic field sensitive and temperature sensitive lines. And then we would need to do a really systematic analysis of these results with spectroscopic, spectropolarimetric and photometric data. Okay, and then there's this discrepancy between these models. If we believe all of the models or all of the inversions in different astrophysical areas, we will be turning schizophrenic very easily. Because first of all, we see these non-axisymmetric features which seem to show some kind of cyclic activity. And this would be consistent with something like an alpha squared or alpha squared omega dynamo. Whereas on the other hand, or some authors tend to see with a different method, more or less axisymmetric fields. Cyclic, nobody really can tell. So what the real problem here is that there hasn't been really a study where people would be using the same observations and then using independent methods to see what they get actually out of the inversion. So what we would need actually in this field, and I very much agree with this, there should be some kind of a benchmark how to test these models, because it's not very good if you have 3 or 4 different methods and they all give slightly different or totally different results.
Wasn't there an attempt in the 90s, 1990, to do that?
Yes.
So what was the result of that?
Actually, we have the same results as those Chinese guys doing.
In 1990?
Same target with different observations.
But that was only temperature inversions.
Yeah.
Yeah.
Okay.
So for these magnetic inversions, no such thing yet exists.
Yes.
Okay, so this is actually the end of my first part. Okay, then second part, I will talk about models, solar and stellar, and stellar here is in brackets because there isn't much to tell about stellar dynamo models. So mostly I will concentrate on different solar dynamo models, and in particular with these 2 different main contenders on this field: flux transport dynamos and then what we call turbulent dynamos. And first I will go through the basic equations, which you should know already by heart. And maybe if there's time, maybe I will say a few words about computing these turbulent transport coefficients in particular in convection simulations. But Matthias Reinhardt will give a much more detailed talk in the afternoon about that. Now, why did I have that one here? Okay, so in the sun we see spot activity, which looks terrible here. We see these spots at latitudes 30 degrees towards the equator, which kind of, when you plot it as a function of time, it kind of looks like a butterfly. And then if you analyze this, where these spots occur on the solar surface, then you find out that the spot distribution is more or less axisymmetric. So there isn't kind of any persistent active longitudes. This is disputed by some people. Some people say that there are, which are active longitudes which last for centuries, even. And but it's not so clear if this is true. There are certainly some active nests which can last for several rotations of the sun. That means several months. But it's at least to my mind, it's not yet fully disclosed, this whole thing, whether there are actually active longitudes in the sun or not. But the main thing is to remember that the solar magnetic field, large-scale field, is more or less axisymmetric. We change us to our equations, and I hope that at least the induction equation is now familiar to everybody. And then we do what people have done here many times in these talks. So we decompose these fields into a mean and fluctuating part, and then apply the Reynolds rules, and then we obtain the mean field induction equation, where we have an extra term, electromotive force, which is just a correlation between the small-scale velocity and small-scale magnetic field. And as discussed earlier, the solar magnetic field is, the mean field is on average axisymmetric. So then we can express our magnetic field by two scalar fields, A and B. And of course, on top of that, we need to know something about the large-scale flow. And the large-scale flow is now also axisymmetric. We have the basic rotation of the star, and then we can have meridional flows, which are just flows going in the meridional plane from the pole to the equator, or vice versa, or both, of course. Now, the simplest form of our electromotive force, now I have not specified what alpha here is. It can be turbulent alpha, it can be some other alpha. It's just that we have two scalar quantities here in our electromotive force. And then we just substitute this back into our induction equation, and this is our equation that we have to solve. Where we have a total turbulent diffusion, or turbulent diffusion plus the molecular one. The molecular one is so small that it can usually be complected. And then we just go into new units. We measure length, which the radius of the sun, or the radius of the star that we want to model. Then we have a new time unit, which is the turbulent diffusion time. Then we choose a unit for the magnetic field here, it's the equipartition field. And then the other units we can derive from this. So the unit of velocity, for example, is turbulent diffusion divided by the radius. And when we do this exercise, we find out that our models then are governed by a number of dimensionless parameters, which we call the dynamo numbers. The usual dynamo numbers C alpha and C omega are here, which just measure the efficiency of the alpha effect and differential rotation. And then in addition, if we have a meridional flow, we can have this Cu, which just describes how fast is our meridional circulation. And here we come to the different types of dynamos. So if we have a situation where alpha effect is very strong, but we have very weak differential rotation, we call these alpha squared dynamos, because alpha goes into all components of the large-scale magnetic field there. On the other hand, if we still have some alpha, but differential rotation is very strong, then we call these alpha omega dynamos. And it just, many times it doesn't mean that you just say that, okay, well, alpha is weak in comparison to differential rotation, but you also neglect the term in the induction equation. For the toroidal field, you get rid of this alpha term, which is justified if C omega is much larger than C alpha. And just on a general note, of course, you have to have, there's some threshold value for C alpha, or for the dynamo number itself, in order to get the magnetic field to grow. And actually this was done done very early by Steinbeck and Krause, already in '69, where they had a model similar to this. Of course, the internal rotation of the Sun was not really known to the same accuracy. At the time, it was assumed that the rotation rate of the Sun decreases when you go from inside to the surface. And then just simple theoretical estimates of alpha effect. You get a positive alpha in the north, and this automatically gives you this equator-ward propagating active regions. And actually, in this model, this was a marginal model, so the C alpha was just on the limit where you can sustain a magnetic field. And the problem, of course, is that if C alpha is, or if the dynamo number is larger, then your magnetic field will grow exponentially, which is not what we see really in the Sun. The magnetic field doesn't grow exponentially until infinity. So you have to have some non-linearity in your equations to stop this growth at some point. And usually it's, well, when the magnetic field grows to be large enough, then it will act back on the flow. And we have two different types of flows here, essentially. We have the small-scale flow, which, at least in the turbulent case, causes your alpha effect. And then we have the turbulent diffusion, which is also the turbulent, or a small-scale effect. But then we also have the large-scale velocity field, and the magnetic field can act back on that. So in principle, if we want to take all of these into account, we should also solve for our velocity field. And this is a complication which is usually avoided by just not solving for the velocity field at the same time and ignoring this kind of back reaction. And the simplest thing that we will adopt here is just that we limit the value of alpha when the magnetic field grows enough. And we use this very simple algebraic quenching formula for alpha. And this is just for purposes to demonstrate how these models work. Of course, we need to have a much more elaborate quenching formula if we want to be anything like realistic. And do we have any observational constraints on all of these parameters? Well, not very much, especially for these turbulent quantities. We don't really know very much. We know that on the surface of the Sun, we can estimate the turbulent diffusion to be something like 10 to the 8 meters squared per second. And if you are using CGS, then you have to multiply this by 10,000. And then we also know that on the surface layers of the Sun, there is a large-scale flow towards the poles. And the magnitude of this flow is about 10 meters, 20 meters per second. And, but this is only known for the very surface layers of the Sun, so something like 20 megameters. And we have absolutely no idea, well, we do have some idea, but we cannot really confirm this with observations, what is happening deeper down. And then for the alpha effect, we have very little information from observations. We can't really just, we can't really look in a telescope, look at the Sun and see what the alpha effect is. So, but we do have some theoretical considerations, but they also give very generous minimum and maximum values for our alpha effect. So minimum is of course 0 and maximum is of the order of the turbulent velocity. And we know that the turbulent velocity near the surface of the Sun is 1 kilometer per second. But if we would have an alpha effect of 1 kilometer per second, this would be very, very nice. But we don't believe that it is that big. And then on the deep layers of the solar convection zone, the velocities are of the order of a few meters per second. And this is actually our order of magnitude of what we usually expect for the alpha effect. 1 meter per second or a couple of meters per second. Okay, so one thing that we do know quite well from the observations is the internal rotation of the Sun, which is known from helioseismology. And what we have is that we have a vertically rotating inner core, then we have this very narrow shear layer, which we call the tachocline, and then we have basically very little radial differential rotation in the convection zone, which is here between 171 and 1 radius. And there's another layer of radial shear very near the surface. And then we have this mostly latitudinal differential rotation. And we need to somehow put this into our dynamo model. And what is usually done is to take some idealization of this. One such thing is presented here. So we have a rapidly rotating equator, slowly rotating poles, and then we have a tachocline, but we have neglected here the surface shear layer. And on the right, you should be seeing something, but you don't see anything. So this is just this is the rotation rate at the pole, 60 degrees latitude, 30 degrees latitude, and at the equator it should go somewhere here. You don't see absolutely anything here, which is a pity. And then there's also the streamlines of meridional circulation. Usually it's assumed that there is only one cell where the flow is going towards the pole at the top and coming back towards the equator at the base. And, well, the observations only give this part, very top part here, and we don't actually know if this is the structure in the Sun. Most likely it's not this structure, because this is probably not consistent with mass conservation. Okay, so then in the solar case we have two main contenders for the solar dynamo. And the first one is what Piali has been talking about in her talks, is what we call flux transport dynamo, which is a dynamo where advection dominates. So in these models the meridional flow is very important for your dynamo, so that it acts kind of like a conveyor belt for your magnetic field, and the turbulent diffusion is so low that there is no connection between the surface and the base of the convection zone. And the connection comes with the meridional flow, which transports the field from the top of the Sun back to the tachocline. And the toroidal field is then generated by the differential rotation in the tachocline of the Sun. And once this field has grown large enough, well, first of all, it's considered that this magnetic field is then concentrated in these thin flux tubes at the base of the convection zone. And once they grow large enough, or the magnitude of this field is large enough, they become unstable and then they erupt to the surface. And there are estimates that the field strength should be of the order of 100 kilogauss for these fields to become unstable. And then when they become unstable and get into the convection zone, then they are essentially immediately transported to the surface of the star by magnetic buoyancy. And this is then modeled in this model, in these flux transport dynamos by what we call a non-local alpha effect, which is just can be represented by an electromotive force where you have you have some magnitude for alpha, some profile, and then it usually acts on the surface. It deposits field on the surface of the star, but it's proportional to the magnetic field at the base of the star, or at the base of the convection zone. And this just models the rapid rise of these flux tubes from the base of the convection zone to the surface. And many times this is called the Babcock-Layton effect, after two guys who were the first ones to suggest this sort of models.
They didn't really know that it was coming from the bottom of the convection zone, right?
Sorry?
They didn't really know it was coming.
No, that's true. So in that sense, it's kind of misleading, this nomenclature. And this is usually the only alpha effect, and there's only a phi component of the electromotive force. So these dynamos are truly alpha omega, because usually the other possible alpha effects, like the turbulent alpha effect, are neglected. Sometimes there is an alpha effect at the base of the convection zone to get a correct parity. In some models, not all of them, but usually these what we call turbulent alpha effects are omitted. Okay, there's just a schematic presentation of this same thing taken from a paper by Barty and Gilliman. So this just shows an example. You have some field lines going that way, at the base of the convection zone. Then you have differential rotation acting on these. So the equator is rotating faster than the poles. So after a while, these are wound up in these kind of loops. And then the instability hits these loops and they erupt to the surface. And then they are twisted on the way by rotation. And then what you have at the surface is that you get these bipolar regions erupting at the surface. And then actually at the surface, in these models, the turbulent diffusion is again increased. So you can have reconnection into these poloidal loops. And then your meridional flow transports this poloidal field back to the pole and then back to the base of the convection zone. And then in the end you have a magnetic field which is switched sign during this process. So this is in a nutshell what these dynamos are doing. Of course, all of this is happening at the same time in the real model, so it's a bit more messy in the end, but that's the general idea. So I just present some representative results from what we call a solar dynamo benchmark, and these are just the profiles of our different. This is the turbulent diffusivity. Now you see that it's one order of magnitude less than what we would expect from surface observations of the Sun. Then we have a steep decline to the core. And here we have what is here called the Babcock-Layton term. So it really acts on the 5 outermost percent of the solar radius. And we have a similar profile for our differential rotation and meridional flow. This one you should neglect because we don't use any alpha effect in this particular model. And then we have an example butterfly diagram. So, okay, now you can't see any of the text here. But we do see equator-ward propagation of the activity belts, and we have a cycle period which is 19 years, which is not far off from the 22 years that we would expect for the Sun. And then here you see an animation of one cycle of this this dynamo. So yellow one is plus. Oh, this is the azimuthal field. the control lines give the radial field isocontrols. And what is very good about this model is that it's fairly simple, and it produces quite easily these solar-like butterfly diagrams. But there are also problems with this model. This low value of eta is quite hard to justify from a theoretical point of view, because we would expect in the solar convection zone from simple arguments to have at least one order of magnitude more turbulent diffusion. And also the structure of the meridional circulation is very important for this type of models. So if we would have more than one cell in radius or in latitude, it would no longer work. And there's also some issues with the strong magnetic fields at the base of the convection zone. So 100 kilogauss cannot be observed. We have no way of observing magnetic fields at the base of the convection zone. So we simply don't know if they exist. And there's another issue related to these large fields in below the convection zone, because there's evidence that these fields are unstable, especially if we have a differential rotation by the Taylor instability. So it's not clear if these large fields can exist, or if they actually do exist in the solar convection zone, below the solar convection zone. Okay. Then we have the other contender, which is, I'm not saying that it's better off at the moment in producing detailed solar dynamo models, what we call, here I call distributed dynamo, which is usually a turbulent dynamo. And these are models where usually diffusion dominates and not advection. And okay, this should be familiar as well. We have the electromotive force, and in our simplest possible case, isotropic homogeneous turbulence, we have two scalars alpha and eta t, and which describe the generation and diffusion of magnetic fields. Here is just a schematic representation what an alpha effect should do. It should produce a current along our initial magnetic field. And this can be done with the help of helicity in the flow. And this equation here is very nice with these two coefficients. But we know that in the Sun, the turbulence is not isotropic and homogeneous. So we end up with a bunch of other terms. In fact, we have to take the tensorial formulation of these two coefficients, which brings us a huge number of different coefficients and different effects. And it's very difficult to know beforehand which one of these effects is the dominant one, or which ones are the most interesting ones. So the problem with these models usually is that you can construct all sorts of different models and taking into account different parts of these tensors. And nobody really knows what are the dominant ones at the moment. So I have a couple of approaches here. Of course, one that I have made myself. So one way to determine these coefficients is to compute these from a 3D numerical simulation. Not a full spherical simulation, but something simpler. We just take a box where we have convection, and then we place it at different latitudes, for example, in the solar, or in some convection zone. We cannot pretend that these are solar-like situations, of course, because the Reynolds numbers and stuff are very, very much below the solar ones. But at least in principle, we can probe these coefficients by using these local simulations. And what we did a couple of years ago was to determine all of the coefficients of alpha. We have 9 different coefficients here, and we can actually represent them by 2 different coefficients. First of all, we have alpha, which is the symmetric part of the what is here the A tensor. So this is just the diagonals of the of our alpha tensor, and then we have the off diagonals, which is the antisymmetric part, and this guy here brings in an interesting effect, which is called turbulent pumping, and it can be, if you put it into the induction equation, it turns up as an extra advection term for the mean magnetic field. But this, you should not consider this to be modification of the large-scale flow. It's just the advection of these large-scale fields by means other than the actual mean flow. So this is a property of the turbulence itself. Okay, so now we can do this for different latitudes, and I fear that this figure will be bad. It's not as bad as I thought. So here we see there's 4 different latitudes and the 3 different diagonal components of alpha. So we see that alpha is highly anisotropic, and here alpha YY, this is now the most important part for the solar dynamo, corresponding to alpha phi phi in spherical coordinates. And we see that this is the pole, this is now 60 degrees, 30 degrees, and this is the equator. So we see that it has almost a constant value in the convection zone, except of course at the equator where it's 0 by symmetry. And this is now something which can be taken into account in our dynamo models. So we can use this as a guide to determine what is the latitudinal distribution of alpha effect, for example. And we can do the same with these other alpha coefficients, and also for the turbulent pumping. And actually we can do this this was done with a Coriolis number of 4, which corresponds to a depth in the solar convection zone, which is basically at the middle of the convection zone. If we do runs where rotation is weaker, this could be considered as a layer which is higher up in the convection zone. If the rotation rate in these models is higher, then we can consider those to be represent the situation at the base of the convection zone. Okay, so that's what we did, and then we put all of these coefficients into our model, and what we get here is just a typical butterfly diagram again. This is now the toroidal field, magnetic field at the base of the convection zone. And we do again see these equator water propagating active regions, and but the cycle period is just half of the solar cycle period. And actually we had to, in this particular model, we had all of the pumping coefficients as well included. And the good thing about this model is that it's not really, it doesn't rely on the meridional circulation, a particular type of meridional circulation, although it helps in this particular case to have this one cell configuration. And then we don't have really a conflict with the theoretical estimates of the turbulent diffusion. At least the magnitude, we don't have a big conflict. But of course, in this case, we were just using a scalar eta t, and didn't take into account any of the other components, because it would be also highly anisotropic in this case. And typical problems for these distributed dynamo models is that, at least in our case, cycle period is too short, so it's half the solar one. It can actually be even shorter if you, sometimes people use 5 times 10 to the 8 meters squared per second for the turbulent diffusion, and then you get even a shorter cycle period. Another common problem is that the activity is at slightly too high regions, so the maximum usually is here around 30, 35 degrees. And you can also have these fields up to 60 degrees or so. Although we did our utmost here to get these magnetic fields towards the equator. And one more problem is that these models can be much more complicated, because we are still missing lots of these turbulent effects in these models. So the problem usually associated with these models is that they are very complicated. You have to, if you want to be really correct, then you have to include all of your turbulent coefficients. And then it's a huge mess. And this is only one possible way of dealing with the turbulence coefficients, transport coefficients. There are, of course, other ways. Maybe the most idealistic way is to just pick your favorite turbulence model and your favorite approximation, then compute the coefficients from that theory, and then use those in your dynamo model. And here is one example, a recent example, where they do exactly this. They also have a meridional flow in this model. And they say that, okay, we get something solar-like, although the period here is too long. And the most interesting thing about this model is that there is no alpha effect. So this dynamo runs entirely on the omega cross J effect and shear current effect, and then the interaction of those with the meridional flow. So there really isn't any unique way of choosing your coefficients in these turbulent models to get something which resembles the sun.
What does that mean for the predictive power if you can take any model and still can recreate the boundary?
Well, that doesn't really help, I would say. I mean, if we don't know the basic mechanism, then it's very hard to make any predictions with these models. Okay, then I have some other models that have been proposed. Yes?
So, when you compute all the coefficients, all the turbulent coefficients, you get values, at least estimates for them, right?
Right.
Can you just do an average value of everything to simplify it, instead of calculating every coefficient for every grid point?
Yeah, actually we don't use the actual you mean this one? This one.
Yeah.
What we actually do, we do take some sort of average of this, of course. And then the latitude, we take, for example, average in the convection zone. Then we get one number. And then we have some points as from different latitudes, and from that we get a latitude profile. I mean, that's the idea. It's not really the idea to use this profile as our alpha in the mean field model. Okay, so some of the other models, maybe in decreasing order of plausibility. So, no offense to Axel, who is not on the top of the list here. So, first of all, we have these overshoot or interface dynamos which work below the convection zone, which are not exactly like the flux transport model. So these can have, these can work off the, again, the buoyancy, but also based on turbulent effects. I think Axel is doing this.
Is the microphone turned off? No.
Overshoots or interface dynamos, and there's a famous example of Parker's, which is not exactly trying to reproduce the sun. And then we have Günther, Rüdiger, and Axel who are doing similar things. And there, actually, it was a turbulent model where the inhomogeneity of turbulence gives rise to turbulent alpha effect and all sorts of things in the overshoot layer. And then we have this is again something that has not really been developed into a full solar model, but there is a suggestion by Axel that the solar dynamo actually acts only in the very surface shear layer of the sun. And that's why I call it the Axel dynamo. And the main idea of this is that, here I say, I'm not saying that it's supported by sunspot observations. I'm just saying that it's not inconsistent with sunspot observations. Which means that usually young spots have the same rotation rate as the sun at this very depth where this surface shear layer begins. And then they tend to slow down when so, now the Axel is in the audience, maybe I create this. The Axel dynamo, which is in the surface shear layer, which is one idea is from the sunspot observations that the young spots tend to rotate faster than the older ones, which would mean that they are seated in a deeper layer. And looking at the rotation rates, this deeper layer would be just where this surface shear begins, which was something like 5% in of the solar radius. And then as the spots get older, they are seated at a higher level, which rotates slower. But as I said, there hasn't really been a full solar dynamo model based on this effect as of yet. And then we have what is sometimes called the Taylor-Sprout dynamo, which basically works off the Taylor instability, or it could be some other instability at the differentially rotating but stably stratified fluid below the convection zone. And their convection plays absolutely no role whatsoever. And but this is maybe not so widely believed to be the source of the solar dynamo, maybe except by Hank Sprout himself. And yeah, I think that's all about solar dynamos. Then I have a couple of slides with stellar dynamos. This is a picture that you saw earlier. And what is different usually in these rapidly rotating early type stars is that the magnetic field is highly non-axisymmetric. So then you have to change your model so that you can also have the phi dimension included. And then I had one more figure here. This is from, why do I have that? Okay, this is just to show that from photometry you can also see this is a very long-term project. Now I can't seem to be able to find the years, but this is a period of something like 20 years or more. Okay, here's the sun, so this is something like 25, 30 years maybe. And these are different stars then. And we see that there definitely are some cyclic variations on many stars, whereas others show very little activity, or maybe there is a cycle, but it's longer than the time series, so we cannot really say for certain. And this is usually, associated with a dynamo cycle. And I'm not really going to show much about stellar dynamo models, because we don't really have that many for stars other than the sun. Here is one example. This is just a mean field model, non-axisymmetric mean field model, where actually also the Taylor number appears. There's also the hydrodynamics included, and this is now increasing the rotation rate to the left, the right, and then increasing the alpha effect when you go up. And these S0, A0, these are just the, this is the symmetric, I mean this is, 0 here is always that it's axisymmetric. Symmetric is that it's symmetric with respect to the equator. And we see that when you go high enough with your alpha effect, then you tend to get these A1 solutions, which are the first non-axisymmetric mode, which is excited. And the same happens when you go to rapid enough rotation, keeping your alpha effect fixed. So it seems that it's plausible from mean field models to expect to have non-axisymmetric solutions when you have a rapidly rotating star. And there have been some attempts.
These are one-dimensional?
No, this is essentially a three-dimensional mean field model.
And non-axisymmetry depends on the alpha square, or the importance of this alpha?
Well, the alpha itself. I mean, the stronger your alpha effect is, then you get the non-axisymmetric modes excited in these models. I mean, you still have some non-axisymmetric contributions, even if your alpha is small. I mean, this is now the dominant mode which is present in these models. So there are also axisymmetric contributions, but they are weak in comparison to these. And yeah, I have just one example of a stellar dynamo model. And the problem, of course, is that we know even less about the stars than we know about the sun, which, I mean, both observationally, and this is a temperature map at 2 different times. This is now the magnetic field configuration from the mean field model. You can consider this lack of information a good thing or a bad thing. The good thing is that if you don't really know that much, then you have more nodes in your model that you can turn and fine-tune the model to reproduce your observations, which are themselves not very certain. But this is not very good in the sense that if you have too many free parameters, then it's not really giving you any more information about the star itself. And this is one example where there's a star called FK comma, and these are two different temperature maps. And then with a dynamo model, it's possible to get configuration where the dominant features are near the pole, and you can have these two different large spots which are about 180 degrees apart in longitude. And yeah, but the problem is that you can find this sort of solutions just by fine-tuning your model. And I think that was. I have a couple of more slides, but these are not really related to this, so I could just go to the conclusions. So maybe I just leave it at that. Thank you.
Any questions, please? Or topic for discussion?
So it is really this diversity of various opportunities, right? Lack of too much freedom. We have too much freedom in your models, right?
Yes.
What can be done about that? Is there any, how you see how it can develop further? Where the same thing can be reproduced in more than one way.
Yeah, I mean, I think it's the last point here in my conclusions that especially if we continue with our turbulent models, we should really use some independent method beyond just our imagination to determine which of these effects are the most important ones. And the independent method, just by comparing, would be to use local numerical simulations, for example, to probe the parameter space and see which one of these effects is the dominant one. And of course, we cannot reach any of the solar values in most of the parameters. But we should do what we can. We can at least probe the rotational dependence of different parameters. And it may turn out that some of these coefficients cannot, or they are so small that they don't really play any role, so we can discriminate some of those at least. And I think this has been an ongoing process during the few past years now. So we know that some effects, at least in the parameter range that we can reach at the moment, some effects can play a role, others cannot. One particular thing is with the shear current effect, which has been a very hotly debated issue in many conferences.
If you assume, just for the sake of playing, that you could measure anything in the sun, right? So suppose you can send a probe and measure stuff. What would immediately discriminate between all these possibilities?
Well, one thing would be very interesting to see whether we have these very strong flux tubes below the convection zone. That would not discriminate any of the turbulent models, but it would discriminate between a flux transport model and the turbulent model, most likely.
In particular, this anticipated very strong field at the bottom, I guess, would be one of the things you would like to really measure.
Yes.
So the field profile as you get closer to the bottom of the convection zone.
Yeah.
I mean, one could, of course, even say that what we observe is a response of the meridional of the torsion oscillation pattern with depth, and this profile is most likely driven by the magnetic field. And so what you see is a decreasing response with depth. Naively, you would say the importance of the magnetic field becomes less towards the bottom. On the other hand, the sensitivity also becomes less. And so we are back with the old statement that if the ignorance increases, then the magnetic field increases, or something like this. So even though it may not actually increase with depth. So that's the problem. Also, I think when Anwar made the statement that, or in his question mentioned that there's a big freedom and everything seems to work, I would think nothing really works well. And that's why, of course, the work is continuing all the time. That's but yeah, you had a comment now?
Well, I was just wondering, how does the magnetic field spectrum look like from the sun? I mean, you just seem to concentrate on the sunspots, but how does the whole magnetic field look like, and how axisymmetric it is?
At every given moment, you mean, right?
Well,
Not average.
Is it possible? I mean, is it too turbulent, or is it?
I don't know.
We can get some idea maybe from the, if you look at a coronagraph, you see the long streaks. You are thinking this could be associated with magnetic field patterns to some extent, but of course it's strongly modulated and affected by the wind at this point. Another thing is looking at these trace images. So you see a lot of arches, of course, across the surface. Can do.
Yeah, I mean, I want to re-mention helicity because it was over and done with last week, but it's not over and done with in the sense that if you are going to base your stuff on anything, the alpha in the convection zone, then you have to worry about that. But on the other hand, I wonder whether these models like the flux transport, you have these tubes, they do exist. Then it's driven completely by Lorentz forces, I guess, right? I mean, buoyancy leads to something breaking out, the twisting is because of Coriolis force, and then the alpha is always that in that sense. So that there's no problem at all.
What did we say this again, really? This is
This is related to the magnetic helicity. You mean magnetic helicity, right?
Yeah, I mean, first is if you are dependent on the alpha effect, in the turbulent alpha effect anywhere, then you have to worry about helicity. That's the first statement. And that, I think, you're probably worrying about it when you're measuring it in various simulations, because it may be suppressed if you don't allow certain fluxes to escape or something like that. That's the first statement. The second statement is in the case of the models where you're basing your alpha effect on the rising and twisting of the strong flux tubes. That you have this same problem because, of course, you will automatically produce an oppositely signed twist in the flux tube when it rides to produce the alpha. But if it's an instability effect, it may not worry you so much, is what I'm just asking.
If it's a what effect?
If it's due to an instability governed by the nonlinear.
Why would it not worry you so much? I mean, the same.
Because magnetic helicity is still conserved, right?
Yes, but will you still get the, you require the twisting of the tube. So if you already have lots of twists inside, then of course it may refuse to twist further. Would it affect you from that point of view? Or in which case you have to worry about it all the time, of course. So since you didn't mention it at all.
Yeah.
I mean, I think one has to worry about this all the time.
Yeah, I think so.
I mean, it's most likely the best method of modeling the back reaction at this point.
Yes, even for the flux transport dynamos, would you have to do the same thing?
One should, one must, yes.
I know that some people in Montana are trying to get
elicit measurements from the analysis of sunspots and try to relate that to the tilt that the bipolar sunspot regions appear.
Yes, but they never use it in their modeling.
No, I don't think that we.
So which worries me.
Yes. All right. No, I mean, as far as we have seen, any large-scale dynamo that is producing magnetic helicity of both, of either sign, the one of the large-scale magnetic helicity is the one which produces a tilt and which produces your toroidal field, which you want for closing the dynamo cycle loop. The other sign is going to produce a dynamo effect which quenches, regardless of whatever present other effect was there. So if you had a Babcock-Leighton effect, then and it produces some magnetic field, then this magnetic field will produce the back reaction wherever that field is, regardless of where you choose to place the Babcock-Leighton mechanism.
Right. Yeah, that's.
So it's a general philosophy then. I'm a bit cautious with my wording, therefore I say philosophy here.
And since we discussed helicity last week and forgot this week, so I wanted to bring it back again.
So, can we make a short list of what is understood about the sun? Then, 22 years for the solar cycle. Can we confidently reproduce this feature? So the models which are realistic enough, reasonable enough, which we can understand, and we do have a period of the order of 22 years.
I don't think we can say for certain that we know it's of that the basic origin lies in alpha omega, because already I can name three possibilities here. The standard one is alpha omega, that produces cyclic solutions.
But of too short
yes?
period, right?
Too short, but that's too short if the alpha effect is and eta effect is unquenched. So that's most likely in ignorance too. So most likely these effects are quenched.
Clear. If it doesn't work, there's something wrong. This is clear. But is there?
But anyway,
if it's too short, there's something wrong.
Yeah, but at least to get a cycle as such, one can have an alpha effect and an omega effect, and the right geometry. But that is not a guarantee as such. Alpha and omega is not a guarantee that it's cyclic, but it can be. The second mechanism is if you have, in addition, meridional circulation, in which case the meridional circulation as a period, as we heard yesterday and a few times last week, is also important in the cycle, or maybe important if that mechanism is playing a role. But we know of yet another third mechanism which produces cyclic solutions with certain boundary conditions, which you may not find realistic necessarily, because it would mean perfect conductor at high latitudes. But with the autodifferential rotation, produce also cycles. So in principle, there are three different ways of making cycles. And if none of them really are appropriate, we shouldn't really jump to any of such a conclusion at this point, I think.
So you won't consider this to be a major problem, fitting the cycle period in the existing models?
If you take the freedom of changing some parameters, then you don't have a problem. No.
Within reason, changing parameters within reason.
Can I ask that question differently? Is there a way to take all the ordinary physical parameter, balls of size r, blah blah blah, temperature, you name it, and get 22 years out of it? Can I dimensionally write t equal something, and then when I finish writing the something, it's in multiple of years? I don't want the 22.
I mean, one parameter, of course, is the turbulent turnover time. That's one thing. The other thing is the non-dimensional ratio, and that's the ratio of the length scale of the turbulence relative to the length scale of the domain. And so that's something where the freedom begins to play a role. You don't exactly know how big your eddies are. You have a big spectrum of eddies.
But you have granulation, have supergranulation.
Yes.
Does any of these scales?
Yeah, right. It's so it goes even quadratically with that scale separation ratio, if not even to the third power. So it's quite sensitive, depending on some details. No, it's a quadratic. And so, so you could say you take your turnover time. That's what I would maybe think of, even relatively short, as short as a day. And then you would have
which is similar to granulation, right?
Yes, and then you would need to go to, which is the supergranulation layer, yeah. And then you would need to have the scale separation ratio squared from the top layers, which is 1 megameter, to the domain size, which is more like 100 megameters. And so this could give you a ratio of easily 100 or a few hundreds.
Then following, the next question is that another major observable, that the propagation of dynamo wave from 30 degrees latitude down to the equator, and additional propagation in the polar regions towards the pole. So 30 degrees latitude, where the sunspots appear, and what, 5 degrees latitude where they disappear, or what, 7, 8?
It's possibly even less. They are very close to the equator that they disappear, right? I think.
So these are also major features, major observable features.
Yeah. I think
Can they be reproduced?
the poleward migration looks very much in the form of individual streaks. So that makes it extremely plausible that that really has something to do with the circulation at high latitudes. It's different, I think. It looks structurally quite different from what you see at the bottom. Yes, all these streaks. These are narrow features which all go poleward. So here,
So just below you can see
and
it.
here too, yes. Relatively high speed, which is, I think that's like 2 meters per second, yeah? Pedestrian speed. Leo Mestel has been saying all the time. It could be even faster, it could be more like 10 meters per second.
So are they understood? Are they understood? Was the
poleward,
nature?
yeah, this is perhaps very plausible, I would think, yeah. That this has to do with circulation. Yeah.
And the range of latitudes, that it starts at 30 degrees and then propagates towards the...
No, that's not clear. Not really, no. Because everybody who's working with the Babcock light mechanism and any mechanism, I think they have to assume by hand a profile of the alpha effect which is concentrated near 30 degrees. So you cannot say it's understood if you actually put it in. I mean, the strongest alpha effect is near the pole.
Well, that depends.
That depends on
the rotation rate.
That reminds you, do you actually have a picture of latitudinal dependence where it shows really goes down towards the poles, the alpha effect?
I can find one.
Yeah, because in one of the talks, I think that came up.
I think that in Piana's model, the alpha it depends on the cos theta, so it will be bigger in the pole too. And it's concentrated.
So there's no sine square factor.
No, I don't think so. Do you remember the stuff with Piana's? I think the
It's cos theta.
it's just cos theta.
Just cos theta.
So it's higher in the pole.
Okay, good. Thanks for pointing that out.
Okay, this is not very good. This figure of mine.
Because somehow people actively discuss active longitudes. But if the active latitude hasn't been explained, discussing finer details, you can discuss these finer details until infinity if you are not sure if your starting point is correct. Right?
So here we have
What we do discussing things.
alpha effect.
Right. And so 180 degrees means the southern pole.
Southern pole, and this is the equator.
Yeah. So it's at least less at the pole, but not zero.
Not zero. Yeah, this is close to the top of the convection zone, and this is from the bottom.
Yeah.
Or in the overshoot.
And that's for the
Rapid rotation.
in Coriolis number close to 10 perhaps, yeah? Or 3 at least.
Yeah, 3 now. It's
The sign of alpha, obtained here, for example, is it consistent with the equator what propagation? For the differential rotation obtained from helioseismology. So is this problem still around?
But look at the, show him the differential rotation pattern, and maybe I should show a more clear one even. Because there's two different signs. There's a negative, a positive sign throughout most of the convection zone, and then there's a negative one near the top.
Yeah.
The one near the top is normally discarded. So for a positive alpha effect, in order to have equator migration, you would need a negative gradient, which you would have only in the top layer.
Or otherwise you have a meridional flow, and meridional flow solves the problem in the base of the convection.
Yes.
Or turbulent pumping.
But it does require, of course, at least two of these other caveats: a low diffusivity, which we don't understand, and the absence of an alpha effect in the lower part.
But actually, what's the skim
I
depth
think we have to
for
have an alpha
22 years
only at the
period?
top.
What is the skim depth for the 22 years period?
That's, I think, on the order of, was it as little as 70 kilometers?
What?
70, I think it's like 70 kilometers.
For ohmic diffusivity, you mean, for ohmic resistivity.
Does anybody remember? I had it probably.
Maximum.
The skim depth for 22 years.
This is a model where we have an alpha effect also at the base of the convection zone. It's strongest at the base of the convection zone. And we have the solar differential rotation profile with meridional circulation. I mean, we have all of these effects here, and it's propagating equator water.
But that's because of the circulation, yeah?
Not only because of the circulation, it also works without.
And why do you
That's okay. We also have turbulent pumping, which is also equator water.
So it's because of the pumping, maybe, mostly, in this case? That you get a quarter of migration?
Yeah,
And Gustavo agrees,
but
yeah.
meridional circulation also helps because it goes the same direction. Goes towards the equator at the base of the convection.
But still, imagine that I have somewhere in the middle of the convection zone a electromagnetic field with a period of 22 years. Between me and that area is a huge layer of conducting media. This oscillatory field may not be visible from the top just because it is oscillatory. This is why I'm asking about the skim depth.
Yeah. I mean, I worked this out.
But for the turbulent problem, for the turbulent diffusivity, for the turbulent conductivity.
Yeah, but that's not relevant.
Is it not?
At least the molecular, I was looking at the molecular one.
This will be small. This undoubtedly will be small. But then, unless you really physically advert this field to the upper layers, I don't care what happens in the depth of the sun. Because of the small skim depth. So should we worry indeed about the overshoot layer? Anyway, it's unobservable. If this is a oscillatory field,
Yeah.
it can do whatever it wants.
Yeah.
We will never see.
I personally don't think we should worry about the overshoot layer. The reason why people do worry about the overshoot layer is because there's an anticipation that one needs to park magnetic fields, which is a strange concept. If you have an oscillator, you don't think you want to park it at the upper edge and then let it down again, and then it parks again for 5 years over there. But that's what some people propose, that you have two parking slots. One at the end. Independence people need to.
But actually, imagine that I have a system, a conducting system, and I have inside the system a electromagnetic field, and the frequency of oscillations depends on depth. What I will see on the surface? I will see the upper layer.
Yes. Perhaps so.
But make it turbulent just to see how much will be the connection between
I
the
agree with
layers.
that. And that's,
Maybe you should look at the surface and no deeper, as you do right now. All of a sudden, I start
yes,
agreeing.
there's a general problem with anything working near the surface in a narrow layer, and that is that the latitudinal extent of the dynamo wave will be at the most typically a factor of 3 more than the vertical depth. That would be very little then. It would be like only 100 megameters, and it's more like 3 or more 100 megameters. So that's a general problem, and it's not clear how to solve that issue. Patty and I have looked at trying to solve that using anisotropies of the turbulent diffusivity. That was an idea, but it didn't seem to be borne out by some simple model calculation that we did at the time. So this is something I think would be important to address. Yes? Anything else? If that's not the case, then we better break for not for lunch, but for coffee. And we thank Petri again for putting
Is it me who is talking now? What? Is it me who is talking now?
No. Yeah, I'm sure. But you can go.
Forget about me asking.
No, you can go.